Hello students, very good morning. Welcome to Narayana Live Classes. Today for class 8 students, we are going to discuss assignment 21 on number system. Okay, now let us start the first question. If n is equal to 2 power 4, 3 square into 5 square, then what is the value of phi of n? What is phi of n for us? Phi of n is what we call as Euler-Lorentzian function. Okay, what does phi of n gives us? Phi of n going to give you the number of natural numbers that are co-prime to the given number n. The number of natural numbers that are co-prime to natural number n, which are less than that, of course. Okay. Now, what is the formula for phi of n? Suppose if you have n as p1 power alpha 1 into p2 power alpha 2 into p3 power alpha 3 and so on. Okay. Phi of n is given as n times of 1 minus 1 by p1 into 1 minus 1 by p2 into 1 minus 1 by p3 and so on. That is a formula to find out phi of n. Okay, now based on this, we are trying to find out phi of n for the given n. Now, n is 2 to the power of 4 into 3 square into 5 square. Therefore, phi of n is n times 1 minus 1 by p1. p1 is 2 here. First prime is 2, second prime is 3, third prime is 5. So 1 minus 1 by 2 into 1 minus 1 by 3 into 1 minus 1 by 5. Okay, that is otherwise, let us write value of n as 2 power 4 into 3 square into 5 square into 1 minus 1 by 2 is 1 by 2. 1 minus 1 by 3 is 2 by 3. 1 minus 1 by 5 is 4. Okay, if you simplify, here 2 let me cancel. 3 and square means we'll have 1 here. 5 cancels here, 1 remains over here. It is 2 power 4, that is 16 into 3 5s are 15 into we have 4. That is going to be 4 into 50 is 16. 60 times of 16 is 960. So out of the given 4 options, the first option is 960. So that is the right option. Okay. Now we move to the next question. If 2 to the power of 341 is congruent to x modulo 341, then what is the value of x? Okay. Now, if you look at 341 we can write as 11 times of 31. 11 times of 31. Now, using Fermat theorem, we have, if there are two numbers a and b whose HCF is 1, means a and b are co-primes, then we have a to the power of p minus 1 is congruent to 1 modulo b. What is that? Where HCF of a comma b is equal to 1, means a and b must be the co-primes. Then a to the power of p minus 1 will be congruent to 1 modulo p. Using that property, let me take modulo 11 and modulo 31. Then by applying certain theorems, I can prove that 2 to the power of 341 is congruent to some value. That value is nothing but x modulo 31, right? Now, let me take 11, modulo 11 let me take. Then by using Fermat theorem, we can take 2 to the power of 10 is congruent to 1 modulo 11. Here 2 and 11 are co-primes because their HCF is 1. So we can write 2 to the power of 11 minus 1, that is 10, is congruent to 1 modulo 11. Now let us raise the power 2 to the power of 10 to nearest multiple of 10, that is 340. So 2 to the power of 34 times, if you raise the power, it is going to be 2 power 340. That is congruent to, even 1 power we have to raise to 34 times. That is also 1. So we can write simply 1 here, modulo 11. But actually what is required now? 2 to the power of 341. So let me multiply both the sides of this congruency with 2. So we have 2 to the power of 341 is congruent to 1 times 2, that is 2 times 2 modulo 11. Let me take it as condition number 1. So 2 to the power of 341 is congruent to 2 modulo 11. That's what we have. Similarly, for 31 modulo 31, let us take. Using the same Fermat theorem, we can say 2 to the power of 30 is congruent to 1 modulo 30. Again, 2 and 31 are prime numbers, so they are co-primes of course. So 2 to the power of 31 minus 1, that is 2 to the power of 30 is congruent to 1 modulo 31. Now let us raise the power of 2 power 30 to nearer to 341. That is nothing but 2 to the power of 330. Okay, if you raise the power 11 times, it is becoming 2 to the power of 330. Is congruent to 1 power 11 is of course 1 modulo 30. Okay, so but 330 means what else you need now? 2 to the power of 11. Because 2 to the power of 330 into 2 to the power of 11 is going to be 2 to the power of 341. So let me take as condition 2. Now let me try to bring 2 to the power of 31 into picture. 2 to the power of 11 into picture. How to do that? We have 2 to the power of 5 is congruent to 1 modulo 31. How can you say that? It's not the Fermat theorem. But here it is purely based on the very definition of congruency modulo. Here 2 power 5 is 32. 32 minus 1. 32 minus 1 is 31. 31 is divisible by 31. So this is obliging congruency modulo property. So we can say 2 power 5 is congruent to 1 modulo 31. Now let us raise the power to 2. So it becomes 2 to the power of 10 is congruent to 1 square is 1 modulo 30. Now you want 2 power 11 here. So 2 power 11 is congruent to 2 modulo 31. It is third property. By using second and third properties, 2 to the power of 330 times of 2 power 11 is 2 to the power of 341. Congruent to 1 time of 2 is 2 modulo 31. So from 2 and 3 what we can conclude? From 2 and 3 we can conclude 2 to the power of 341 is congruent to 2 modulo 31. This is condition number 4. Now let us observe condition number 1 and condition number 4. If you observe both the conditions, 2 to the power of 341 is congruent to 2 modulo 11. 2 to the power of 341 is congruent to 2 modulo 31. Therefore, what we can say is from 1 and 4, we can conclude that 2 to the power of 341 is congruent to 2 modulo 11 into 31. Because 11 and 31 are primes, this property holds good. So, that is otherwise 2 to the power of 341 is congruent to 2 modulo 11 times of 31 is 341. So here in place of here, okay, 2 to the power of 30. So here we have 2 is the right answer. So third option is the right option for this particular question. Okay. Now let us go to the next question. The remainder when 24 to the power of 1947 is divided by 17. So 24 to the power of 1947 is divided by 17. For that, let us start in this way. We have 24 is congruent to 7 modulo 17. How can you say that? 24 minus 7 is 17. 17 is congruent to 17 is divisible by 17. So this property holds good. Okay. Now let us talk about, let us take modulo 7 and based on that we are trying to get the result. Now we have 7 to the power of 16 is congruent to 1 modulo 17. How can you say that? By Fermat theorem. Here 7 and 17 are prime numbers, so their HCF is 1. So we can say 7 power 17 minus 1, that is 7 power 16 is congruent to 1 modulo 17. Now let us try to raise the power of 7 power 16 to nearest 1947. For that, what to do? Let us divide 1947 with 16. So we get 16, that is 34, 2 times that is 32, 27, 1 time that is 60, so it is 11. So if 1947 is divided by 16, the quotient is 121 and the remainder is 11. So let us try to raise the power of 7 power 16 to the quotient, that is 7 power 16 4 power 121. 7 power 16 4 power 121. That is equal to 1 power 121 is nothing but 1 modulo 17. Modulo 17. That is otherwise 7 power, what it will be? It will be 1936 is congruent to 1 modulo 17. What else you need? 1936 means more 11 is required. Let me take it as first condition. I need to get 7 power 11. 7 power 11 is congruent to certain value modulo 17. Then using this condition, that applying condition, we can get the resultant answer. So for that, let me take 7 square. 7 square is congruent to minus 2 modulo 17. Why? 7 square is 49. 49 minus of minus 2, that is plus 2. 49 plus 2 is 51. 51 is divisible by 17. So this property holds good. Now let us raise this power to 10. 7, that is 7 whole power 5 you do, you get 7 power 10. That is congruent to minus 2 whole cube. That is nothing but minus 32 modulo 17. Okay, but minus 32 we can write as 7 power 10 is congruent to plus 2 modulo 17. Modulo 17. So both the sets let us multiply with 7 so that you get 7 power 11, that is 7 power 11 is congruent to 2 into 7, that is nothing but 14 modulo 7. It is condition number 2. Condition number 1 is 7 power 1936 is congruent to 1 modulo 17. Condition 2 is 7 power 11 is congruent to 14 modulo 7. By using 1 and 2, 7 power 1936 times of 7 power 11 is nothing but 7 power, let us write it from from 1 and 2, 7 power 1947. So 7 power 1936 into 7 power 11 is 7 power 1947 is congruent to 1 into 14, that is 14 modulo 17. Okay, so this is what we have. Here we have like 24 is congruent to 7 modulo 17. So 24 power 1947 is congruent to 7 power 1947 modulo 17. We got 7 power 1947 modulo 17 as remainder as 14. So even in the case 24 to the power of 1947 also we get the remainder as 14. So the 14 is the remainder when 24 to the power of 1947 is divided by 17. So first option is the right answer for this. Okay. Now let us go to the next question. The number of integers from 1 to 2001 that are relatively prime to 2002 is. Let us take the number 2002. Let us try to write it in its standard form. So let us divide with 2 so that we got 1001. Let us divide with 7. So we have 7 ones, 34 times, and just 3 times. So divide with 11 so that we get 13. So 2002 we can write as 2 into 7 into 11 into 13. All are primes. Now what do you need now? Phi of 2002. Phi of 2002. What is the formula? 2002 times of 1 minus 1 by 2 into 1 minus 1 by 7 into 1 minus 1 by 11 into 1 minus 1 by 30. That is otherwise 2002 times of, it is 1 by 2, it is 6 by 7, that is 10 by 11 into 12 by 30. See, 2 into 7 into 11 into 13 is nothing but 2002. So 2000 to 2002 cancels. And we are left with 6 into 10 into 120. That is 60 times of 12. That is 720. So phi of 2002. What is phi of 2002? The number of integers from 1 to 2001 that are related with prime of 2002. That is given by phi of 2002. So the answer is 720. That is nothing but the second option. Okay. That is the end of this assignment. Thank you. Have a good day.